Hi. So in today's lecture we'll actually start with the main subject at hand, namely smooth manifolds. So the idea of a manifold, broadly speaking, is, so we want to talk about spaces. So I'll be somewhat vague to begin with. Spaces which locally resemble open sets in Euclidean space. Well, this statement is not meant to be taken literally, but just as a motivating remark. Now, so for instance, we would like to allow things like, so in dimension, there is a concept of a dimension of a manifold. In dimension 1, we allow something like this, which is a circle which is slightly bent at one point, or we can have just an open arc. It can even be disconnected. The union of these two pieces we would like to allow. What we don't want to allow is, so all this is okay. We want it to be okay. What we don't want is something like this, or circle with a spike sticking out and this sort of 8. So we don't want to allow these two. And if one this is just in dimension 1, and similar considerations apply in higher dimensions as well. For instance, in dimension 2, I would like a sphere which is flattened, or just the regular sphere S2, or I'll describe what this is later on, and or just the plane. All these are fine, but what is not fine is something like this. So if you take two spheres in R3 and they touch at one point, or if I take a sphere and put a line on it, so these we don't want. Now there is an easy way of sort of picking out the ones we want from the both in dimension 1 or any dimension for that matter. Namely, if you just look at it closely, one notices that in the first 3 examples, whatever point one takes, even if I take a point here for instance, close to that point, the space I have just looks like a bent arc. So we can define a bijection, continuous bijection from this arc into an open interval inside the real line. And same thing can be done for the other two as well. But in this other 2 examples, if one, for instance, in the first example, if one looks at the point of where these two, where the figure 8, the 2 circles meet, if I stay close to that point, stay close meaning So I will be picking out something like this, a cross. Well, a cross cannot be, there is no continuous bijection from a cross to an open interval. It's something more than a continuous bijection that we need, namely we demand that the inverse should also be continuous. I will formally define that, but for the moment let us just think of it as a way of deforming this to an open interval in a bijective manner. This cannot be deformed to this. There is no way of getting rid of the cross, the point of intersection. Formally a proof can be easily given just by saying, by considering the fact that the interval is connected. Rather, if that will not help us much, but rather if I remove a point here, this problematic point from this space, I will get 4 pieces. More formally, I will get 4 connected components. Now this point has to go somewhere on the open interval if there is such a map, and if I remove this point here, it would correspond to removing some point here, but I will be just left with 2 pieces, 2 connected components. And basically this more or less gives a proof that this cannot be homeomorphic to an open interval, and similar argument will apply for this space as well. So I won't go into that, but now the thing is, even here in dimension 2 the same considerations apply. So how to formally define spaces which are have this property that if you stay close to that point, we get a neighborhood which is like an open subset of Rn. So essentially we use the concept of a homeomorphism. But even before that, I need to start with a concept of a space. Now generally the most general notion of a space that one encounters in a first course is a topological space. So I will assume that it's one knows the definition of a topological space, though in this specific matter one does not actually need that. It turns out that metric spaces are enough. So let me give first the topological definition and then make a remark about metric spaces. So definition. So as I said, I need to first define the concept of a homeomorphism. So let X and Y be topological spaces a homeomorphism F from X to Y is a continuous bijective map such that F inverse from Y to X is continuous. So recall that we had talked about diffeomorphisms earlier between open subsets of Rn. So a diffeomorphism, for a diffeomorphism we had demanded that F itself is C1 bijective and F inverse is also C1. Of course C1 would imply continuity. So a diffeomorphism provides an example of a homeomorphism between open sets, but that is a very restrictive type of homeomorphism. So in the definition of a homeomorphism, there are no considerations of differentiability and so on. Now again, one should be there are examples where a map can be continuous bijective but inverse need not be continuous. So one has to impose this condition. However, I don't want to dwell too much on this because soon we will be moving in talking about differentiable stuff. So let's just take this definition and then proceed to define the notion of a topological manifold. A topological manifold of dimension n is a Hausdorff second countable topological space X such that now this Hausdorff and second countable are technical assumptions, but the important thing is what I am about to write down now, such that every point P in X has a neighborhood U which is homeomorphic to an open subset of Rn. This precisely, so this property, the property that it has a neighborhood which is homeomorphic to an open subset of Rn is usually referred to as we usually say that the space X is locally Euclidean. Now this as I said, one has to put these conditions Hausdorff and second countable. So let me quickly tell you what second countable is. The same thing as saying X has a countable basis. So for its topology, as I said, it's a theorem that in fact if one starts with a topological manifold, in fact one can restrict oneself to metric spaces because of the following fact. Any Hausdorff second countable locally Euclidean again I should emphasize that locally Euclidean just means that every point has a neighborhood U which is homeomorphic to an open subset of Rn. Second countable locally Euclidean topological space is metrizable. In other words, let us give it a name X. In other words, there is a distance function d on x such that the topology induced by d, every time one has a distance function, it induces a topology, the metric topology, namely the distance function defines open balls in X and use that as a basis, and you will get a topology. Note that the topology induced such that the topology induced by D coincides topology. So, we started with a topological space. So, there was a topology to begin with. What we are saying is we can put a distance function such that the topology induced by the distance function is the same as the original topology. So, in short, because of this fact, I can just and notice that the moment you have a metric space, the topology is automatically Hausdorff. It turns out that second countable is the same thing as separable for a metric space. So, if one is not too comfortable with topological spaces, alternate definition of one can work with the following alternate definition of topological manifold. Dimension n. So, I no longer have, I start with a metric space X, a metric space I no longer have to specify Hausdorff, X a metric space. So, actually here I'll just add X a separable metric space. In other words, it has a countable dense subset, a separable metric space which is locally Euclidean of dimension. So, this is equivalent to the original result because of the fact that I mentioned earlier. However, even though topological manifolds are interesting in their own right and they are studied extensively in geometric topology, what we are interested in is we would like to do calculus on manifolds. So, in other words, we would like to talk about differentiable functions, vector fields, flows and so on, tangent spaces, etc. So, we need the notion of differentiability. That does not come with just this. So, I will make another definition which at first sight is not clear why things are defined like this, but I will explain shortly the need for this definition. So, we will say that M is a smooth or C infinity manifold of dimension n, or just instead of writing manifold of dimension n, one normally writes just n manifold. M is a smooth or C infinity manifold. I will use the word smooth and C infinity interchangeably. In my preliminaries lectures, I was focusing mainly on C1 functions. Henceforth, when I say smooth, I mean C infinity, infinitely differentiable. So dimension n if M is a topological manifold such that now in order to state what is going to come here, I need to make a small definition here. So when I have this locally Euclidean of dimension n, I have a chart, so I have a open set. So I need to make one more definition. So I'll try to sneak it in here. In the definition of locally Euclidean, I have this open set U and a homeomorphism phi from U to some open subset of Rn. So this U is in X and phi is a homeomorphism. So this pair is called a chart. And if a collection of charts U alpha, phi alpha indexed by some alpha which covers X is called an atlas. So this notion of atlas is not that important for us, or rather however we'll be using charts very frequently. So a chart is just a open set and a homeomorphism onto an open subset of Rn. And a collection of charts which covers X meaning that every point should be in one of these charts. Such a collection is called an atlas. Now with these two definitions, what I want is that such that if every time two charts intersect, I want something to happen. If U alpha, phi alpha and U beta, phi beta are charts with U alpha intersection U beta not empty. So the picture is like this. I'll continue on the next page. So I have, well, so this is U alpha, this is U beta, and they have some intersection. Well, I also have this homeomorphism and another homeomorphism here. Now this homeomorphism phi alpha will map U alpha to some open subset of here. These are in Rn. Now let's look at this intersection. This is U alpha intersection U beta, under this homeomorphism phi alpha, this gets mapped to some other open. Notice that phi alpha is a homeomorphism, so it's continuous and continuous inverse. So that implies that phi alpha takes open subsets in X, rather open subsets of U alpha to open subsets of Rn. So in particular, this goes to some open subset which is phi alpha U alpha intersection U beta, that is this part. So let's just, that is this, and this goes to another open set. The same thing goes to another open set under phi beta. Of course, this is phi beta of U alpha intersection U beta. So I have two open subsets of Rn now, phi alpha U alpha, this one as well as this as well as this. And what I can do is I can start with a point inside this open set here, I can start with some point here and apply phi alpha inverse. I'll end up with something here, then apply phi beta, then I end up with the corresponding point in this. So let's write that down. So phi alpha inverse composed with phi beta will map, is we can regard as a map U alpha intersection U beta mapping to phi beta U alpha intersection U beta. The point is that these are now both in Rn, open subsets of Rn. I still haven't defined the condition. I said such that something happens. Well, the condition is that this map phi alpha inverse phi beta is C infinity. Notice that it doesn't make sense to say that phi alpha itself is C infinity or phi beta is C infinity, because the notion of a differentiable function makes sense only when the domain is an open subset of Rn. The domain of phi alpha domain is an open subset of Rn and the target is some Euclidean space. But phi alpha is its domain is an open subset of some metric space or topological space. Similarly, phi beta. So to talk about differentiability of phi alpha or phi beta in our usual sense is well, it doesn't quite make sense, but this phi alpha inverse phi beta is a map from between open subsets, and it's perfectly fine to talk about C infinity. This has a name. So this is called a transition function. So these transition functions, they are defined whenever you have two charts which have a non-empty intersection, you get a transition function. And everything hinges, so on these, The whole notion of a smooth manifold is crucially involves these transition functions. Now why does one bother to define it in such a complicated way, the notion of a smooth manifold? But before that, let me give some examples of smooth manifolds. A trivial example is M is just an open subset of Rn. In this case, so remember that to show that something is a smooth manifold, what we have to show two things. One is, well, actually three things. One is it's a separable metric space is one thing. Either that or Hausdorff second countable. Those are usually quite straightforward to check. The more non-trivial thing is locally Euclidean. That's the second condition. The third thing is that this transition functions are C infinity. So in fact, let me just, before I start with the examples, let me just write down that what we have to show. Suppose we are given some set M is a smooth N manifold. We have to show, we have to check the following. First one, if we don't have a metric, natural metric, if M is given as a topological space, we have to show that it is Hausdorff and second countable. Or if it comes with a metric, we have to show that it is separable. It has a countable dense subset. Second thing is M is a topological, M is locally Euclidean. Just complete. M is locally Euclidean of dimension n. This is the second step, is the main step. So what this means, to again to remind ourselves what this means, we have to start with some point in any point in M, and we have to put it inside an open set and construct a homeomorphism of that open set to an open subset of Rn. Well, that's not enough. Then once we do that, we get a whole bunch of charts and an atlas. Then we have to check that transition functions are C infinity. So these are all independent steps one has to verify. Okay, so we'll stop here and I'll begin with examples next time. So we'll check that these three conditions are satisfied in some simple cases. Okay, thank you.